Do y'all use those recordings sometimes? Yeah, okay. Evaporation is really what form of heat transfer? Let's try that as a quicker question. If you were to guess, you can probably reason it out. What form of heat transfer does evaporation depend upon? Does it depend upon conduction, convection, or radiation? Remember, conduction requires contact between two surfaces. Convection requires the flow of a fluid, and radiation is the light that is emitted by an object of a certain temperature, the infrared light. So evaporation is really what sort of heat transfer? Okay, good. All of you, you're evenly split right now between A and B. So I'm going to go ahead and get rid of C. The answer is not C. It is either A or B. And you're still evenly split. But it's not both A and B. All right, I'm going to stop here at 55. All right, it is really a form of conduction. But I can understand why you would put convection, because you think of little Chad Young sitting in front of the fan with no air conditioner, right? Because that makes you feel a lot cooler. And that does assist in the sweating process, because when you stand in front of a fan, then it actually makes that sweat evaporate more quickly, but it's not essential to sweating. So if you imagine, say this is my arm, fat fingers. This is my arm, and I have a little sweat droplet right here. That sort of looks like a wart, doesn't it? But energy goes into it. Energy goes into that because it has contact between the two surfaces. And then that makes it go into a vapor and vaporize and takes that energy away. Convection does help. That's why we use fans, because convection helps that sweating process. It actually takes the sweat away more quickly, especially around here where it's so humid that when we sweat, it just, instead of evaporating off of our body, it just stays on our skin because it's so humid here. And so that makes it more difficult for our bodies to cool themselves. Okay? You'll follow me? Conduction? Convection helps, but primarily it's a conduction phenomenon. All right. The amount of total heat loss in the body, conduction and convection from the body is about 20%. That means the amount of heat loss that I'm losing by touching things or by having a fan blow on me. I lose about 20% of the thermal energy created by my body. Radiation is a lot more. It's 50%. And evaporation is about another 30%. This, by the way, the fact that this radiation loss is so big, that's why they use those space blankets. You ever seen those space blankets? You know what I'm talking about? You see the marathoners after they're done with a race, and they have these little thin foil-like blankets that they wrap around them. Those are space blankets. I don't know why they call them space blankets, but they're really thin and light. And what they do is if you've lost a lot of heat and you can wrap this blanket around you, is the infrared radiation tries to leave your body and then it's reflected back on you. So it's just like having a mirror around you that's reflecting the heat back onto your body, or reflecting that infrared radiation. Typically the body produces about 100 watts of heat, so you're all about like a 100-watt light bulb. Okay, so heat gain and loss. 6 examples of things that you can do to affect your heat gain and loss. The first thing you can do, or one of the things you can do, is you can take cool or hot showers. It's a good idea to take cold showers. Actually, there's this guy, he has a podcast, the Get Fit guy, and one of the things that he talks about to increase your metabolism, I know that nobody does this, but is to take a cold shower instead of a hot. You take cold showers? Yeah, sometimes I do. Like especially if I've been at the gym and really hot, I'll take a cold shower just to try to cool off. But and sometimes at night, I told y'all like how I'm a lot warmer than I used to be, right? I told y'all that after lifting weights and you increase your muscle mass and your metabolism goes up and you're just warmer than you once were. And so at night sometimes, my wife on the other hand is always cold. And so at night she has like 4 blankets piled on top of her and I have no blankets at all and I'm just burning up. And so often before bed I'll just take a cold shower just to sort of cool down before I get into bed. So you can really affect your body temperature in that way by taking cold or hot showers. Anyway, the Get Fit guy says that you can increase your metabolism by taking cold showers. Why would that increase your metabolism? By taking a cold shower. Your body has to work harder, right? Because your body, a lot of the work that your body does is just to keep your core temperature up. And if you're taking a cold shower, then you're decreasing your outer temperature and you're losing thermal energy. So you can take a cold shower. As cold as you can stand, he says. Which around here, cold showers are not really that cold because the bayou's pretty warm where we get our shower water. You can drink hot or cold liquids. Like tea or I don't know, cold water. You can insulate the body. I had a colleague we used to work together. She was from South Korea, and she would commonly drink just hot water because she didn't like tea or coffee. And coffee is probably not the best thing because it dehydrates you. But she didn't like tea or coffee, so she would just drink hot water when she was cold. She just had a coffee cup, and she would, drink hot water. You can insulate the body. You can have forced convection. That's just a fancy way of saying you can have a fan on you, like, 10-year-old Chad Young was standing in front of the fan. I remember when we first got an air conditioner, it was a window unit, and we would just sort of stand in front of it, just amazed at the cold air that was coming off of it. My dad, in 1984, he got a vehicle that actually had air conditioning in it, and it was a remarkable thing. And we could ride around and actually have air conditioning in our vehicle. But he didn't use it because he thought it took too much gas, that his gas mileage was not good enough with it. You can do evaporation. That's sweating. Or have you ever been to the New Orleans Zoo on a hot summer day? What do they have that helps with evaporation? The mist, right? Don't they feel great when you're really hot? You can walk through those mists. Not only do they have a mist, but they have a fan too. Because if you just mist yourself in South Louisiana, you're just going to get wet, right? It might make you cool off a little bit, but really you have to get the water on your skin and then get it off of your skin. So that's really where you cool off more, is when you have that latent heat of vaporization being pulled away from your body. In other parts of the country, we use air conditioning, but in other parts of the country they use swamp coolers. You ever heard of a swamp cooler? It's sort of like we use a similar thing here in between Beauregard and Go Hall. Like all of campus up here, this part of campus is cooled by water, not by other refrigerants like Freon. And what they do is they have, it's kind of cool actually. Let me just draw a little figure. They have like these cooling towers, these big things. That's that big structure in between these two buildings over here. And then they take water and it trickles down. And as it trickles down, it cools off because part of it evaporates and pulls energy away from the liquid water. And so when it trickles down this cooling tower, then it's quite cold. And then they ship it around to all the buildings where it's used to cool the buildings. Do y'all know that? Yeah, so these are all water cooled, not Freon cooled, the buildings here. And they can get quite cold. And swamp coolers are a similar thing, except houses just have like one of these things in between here, but it's a lot smaller. It's like the same size as an air conditioning unit. But you have to live in a place where it's really dry. You have to live like in California or the Southwest or somewhere where it's really dry. Okay, and then finally, heat gain and loss by radiation. For example, from the sun. that you can just, if you want to warm up, you can go sit out in the sun. Okay, so the body regulates its temperature. Remember, this is called homeostasis. Oh, there's something I wanted to show you. Oh, no, never mind. So the brain can increase or decrease the amount of heat that's generated based on these heat receptors. So there are these, we'll talk about this when we get into electricity, but in your body there are these cells, and they just say, hey, your body's too hot or your body's too cold, and then they send a signal to your brain, and then your brain sends a signal to do several things to prevent heat loss. One of those is blood vessels in the skin will contract. You know, they get smaller. Blood vessels get smaller. That means that there's less blood flow to the skin and less heat loss. The second is you can shiver. And shivering prevents heat loss, or shivering actually produces heat. And your body can also release chemicals to increase your BMR. Okay, and if you increase your BMR, that will produce heat. And then there are a lot of voluntary actions. Your book gives some of them. I listed some. What are some voluntary actions to produce or to prevent heat loss? What's something you can do? If your mama tells you, or if you tell your mama you're cold, what's she tell you to do? Go get a blanket, right? I'm not going to turn the heat up. You're going to blanket up. Put that on. So I don't tell her that. Like, I don't even mean what I'm thinking it. Put the jacket on. It's hot. You can drink hot or cold liquids, right? Or hot liquids that can improve your heat loss. I guess isn't really appropriate, but right? You can sort of get closer to somebody, right? What do you call that? You can snuggle up with somebody, right? That's where that's heat loss. A person or an animal or whatever. So lots of voluntary things. Your book talks about those. There are also some ways to enhance heat loss that your body does involuntarily. So to have more heat loss, if contracting of blood vessels conserves heat, what else could you do? Or what else could your body do? Right, they could dilate. So your blood vessels will dilate. On the skin, right? The skin blood vessels will dilate. That allows more blood to go to the surface of the skin, and so your skin is just a lot warmer, and it releases that heat to your surrounding environment. You can also sweat, and those are involuntary. All right. Hyperthermia, I think this was on the quiz last time. Body temperature is too high, and hypothermia, body temperature too low. The hyperthermia can result from two different things. I'm going to list those here. The first is it can result from a fever. Right, so just your body is producing white blood cells. You can produce more of those when you have a fever. To fight infection or whatever the issue is. The second thing for hyperthermia is exertion dehydration. So your body is not able to cool properly. That's why in that football, the NFL camp, that they tell them that you need to drink plenty because your temperature is so high and your body needs to be able to cool effectively, and it can't do that if you're not hydrated. You need to drink lots of water. Okay. Let's try this question. The one on the left. I'm going to remind you the equations that we had before, our calorimetry equations. Q equals mc delta T. Q was equal to m times LV, or Q was equal to m times LF, where the LV is the latent heat of vaporization and LF is the latent heat of fusion. So if a person sweats and you have 0.1 kilograms of water that evaporates from your skin, that would be 100 grams or 100 milliliters of water, then how much heat is dissipated through that evaporation? Okay, a lot of you have the right answer now. I know it seems complicated. There's a lot of words and a lot of numbers up there, but once you get into it, you know which equation to use, which numbers to use, then it's really not that difficult. If you finish this one, go on to the next one. We'll do maybe 10 more seconds on this, stopping at 140. All right, good. B is right. So what you need to recognize here is, first of all, the amount of heat that I'm losing due to evaporation is going to be mostly this mass times the latent heat of vaporization. Some energy goes into the sweat just to take it up to a certain temperature. Like if the sweat is cold, or if you have water that lands on you that's cold, your body will heat it up. But almost all of the energy goes into vaporization, actually vaporizing that. So the mass of the water that I have was 0.1 kilograms. And then the amount of the latent heat of vaporization I give you here is 500 kilocalories per kilogram. And so the amount of heat that's lost then is equal to 0.1 times 500, or 50 kilocalories. I would expect something along those lines, or this next question for the test. Like I said, I know it seems complicated. There's a lot of numbers and sort of a lot of words in there, but if you know which equation to use as far as the latent heat of vaporization in this case, then the math isn't really that difficult. Let's try this next one. I want to raise the temperature of water from 37 to 42 degrees Celsius. How much energy is required to do so? What is Q for me to raise that temperature by 5 degrees Celsius? And I give you the various values there. All right. If I want to figure out how much energy is required to raise the temperature of something, which of these am I going to use? Am I going to use this Q equals mc delta T, the mass has latent heat of fusion, or NLF? Which one do I use? The first, second, or third? The first one, right. I mean, that's really the only one with a change in temperature. Right? What is my change in temperature for this material? What's delta T? If it's going from 37 to 42, what is my change in temperature? It's 5, right? 42 minus 37 is equal to 5. And then, what is C? What do we call C? What is C? This is a specific heat, right? So C is our specific heat. So this is what I'm going to need to be using. I know the mass, I know the specific heat, and I know the change in temperature. So I want to find what is the energy required to raise that temperature. I'll give you a few more seconds to think about that. I'll stop at 2:15. All right. Some of you are just using this latent heat of fusion. I think maybe you thought, oh, well, I didn't use this equation before, so I'm going to use it now. But that's not true. You want to use this. Anytime I give you a change in temperature and I ask you for the heat, then I'm going to be using that equation. So my delta T, I first want to find, that's TF minus TI. In general, delta is always going to refer to that, a change in something. The final minus initial, that's 42 minus 37. That's equal to 5 degrees Celsius. The specific heat is equal to 1. And now the mass was 2 kilograms. So I say Q is equal to M. That's 2 kilograms. 1 kilocalorie per kilogram degree Celsius. Times 5 degrees Celsius. I can look at how my units all cancel out here. Those all cancel out, and I'm left just with kilocalories. So this is equal to 2 times 1 times 5, which is 10 kilocalories. Be prepared for 2 or 3 or 4 questions like that on the test where you're calculating the energy required to either change transitions or to raise the temperature. And so you'll need to be able to identify if it's a transition change. Am I using the vaporization or the fusion? Like, am I going from a liquid to a gas, or am I going to a solid to a liquid, or a liquid to a solid? Okay, so you need to identify which that is. As far as the using the calorimetry equation, you just need to look at, okay, I'm just changing temperature here, so I use this. I'm not changing phase. Okay, y'all can do that for me on a test? You can. I want to practice, so on the old test there are some practice questions, so make sure that you can do it on your own. If you can't, come see me. I'm willing to help you. I can sit down with you for a half hour or more, and whatever you need to get it. All right, a couple more things, then we'll move on to the next chapter. Oh, this was just an example. Your book went through this example. I'm going to show it to you sort of for, I don't know, for your reference. You're not going to have a question like this, but I'll just show you because it's related to what we were doing before. So you consider a feverish person. With, say, 104-degree fever, and you put them in an ice bath or a tub of water to cool. How much energy must leave the person in order for them to cool properly? So kind of like the bomb calorimeter with the little piece of fruitcake inside of the water, except in this case it's the person is inside of the water and they'll raise the temperature of the water. But how much energy has to leave their body for them to actually bring their fever down? So if you imagine your person is undergoing this temperature change, the mass of a person is about 70 kilograms. So for a person, our mass is about 70 kilograms. Their temperature is about 104 degrees Fahrenheit. That's going to be their initial temperature. But you want their final temperature to come down to about 98 degrees Fahrenheit, 98, 99 degrees Fahrenheit. That's approximately what in Celsius? Your body temperature in Celsius? 37. That's a number you need to know. Likewise, you need to know the room temperature. Room temperature, 70 degrees, is about what Celsius? About 20, right. You don't need to know this, but it's more than 37. It's about 40 degrees Fahrenheit, or 40 degrees Celsius, rather, if you have a fever. remember, I think this was on the quiz. Maybe it wasn't. But notice here the Fahrenheit and the Celsius temperature scales, that there is a 6-degree difference between these two temperatures, but there's only a 3-degree difference between the Celsius temperature. Because remember, the Celsius change in temperature for Celsius is bigger than the change in temperature for Fahrenheit. And remember that was early on in this chapter, that the Fahrenheit scale and the Celsius scale, they were both based on the same reference points, the boiling and freezing points of water, but the Fahrenheit scale had a lot more tick marks in between those two, like was it 212 to 32, so 180 tick marks, whereas the Celsius scale only had 100 tick marks between. So the Celsius degree is bigger than the Fahrenheit degree. And we can see that here in these differences in temperatures. That's about a factor of 2 almost, actually. All right, so I say 70 kilograms. The specific heat of the body is really close to that of water. The specific heat of water is 1. The specific heat of your body, which is a lot water, is 0.84. That's kilocalories per kilogram degree Celsius. And the delta T is 3 degrees Celsius. And so that works out to be negative, actually this is not 3, it's negative 3, because TF minus TI is 37 minus 40, or negative 3. So that works out to be negative 176 kilocalories. That's how much energy needs to be taken away from your body in order to reduce your temperature. And that assumes that your body's not doing any additional things to keep pouring heat into your body, right? Which it is. Right? It's producing those white blood cells that are sort of triggering the feeder to produce those white blood cells. No problems like this on a test, but there are a lot of things here that we've talked about already that will be tested. So you will have to do a problem where you're figuring out the heat due to change a substance, but it'll be a little simpler. The numbers will be a lot simpler to deal with, like the one we just did. I don't know why I want to do this. It's just really doing the numbers. I don't know that it's real helpful. Is that okay? Did not do this one. And then energy imbalance. Your book goes into the conduction. It just sort of goes through, gives you numbers for K for your body and the area and the width and all that. And then your book also talks about energy imbalance. That dieting can be really complicated, right? It is, that your body is very complex, and the way our body responds to food and exercise and all that is really complex. But energy imbalance is fairly simple. That if you use more energy than you consume, more energy, then that means weight loss. That's a simple fact, that if I use more energy than I consume, then that's weight loss. So if I consume more energy than you use, then that's weight gain. But there are lots of different factors that can contribute. High-carb diets have been shown to lead to weight gain, for example. Lots of sugars and stuff, carbs turn to fat. Genetic issues. Lots of different factors that contribute, and that's sort of beyond this class. But some of y'all will take classes just on that. Okie dokie. Let's go to the end of chapter 3. Kind of a fun chapter. Any questions, John? Let's do a few quick clicker questions in the back of the chapter, sort of see where you stand on some of these issues. Return to the back. I don't have page numbers. It's in the back though. It's exam 2.
It's like it's a one, so it doesn't have.
Yeah, it doesn't have. But there's exams 1, 2, and 3 in the back of the book. All right, let's try this number 20 right here. Consider this roller coaster. At which position does the cart have the most potential energy? A, B, C, or D, or does it have the same potential energy at every point? If you finish number 20, go on and answer number 21. We'll do that next. All right, let's wrap this up in about 5-7 seconds. 53, I'll stop, 53. Oh, was that a sneeze or a hiccup? Hiccup, that's okay. All right, A is right. It has the most potential energy at point A because it's dependent upon the height. Remember, potential energy was equal to M times G times H. At which location does it have the highest speed? Same options, A, B, C, or D, or does it have the same speed at every location? All right, I'm going to stop at 33. 33. Good, B is right. It has the same speed down here. You know that because U is 0, basically, because H is equal to 0. So all the energy that it had up here is now kinetic energy down here. It's transferred. It used to have a lot of potential energy and no kinetic energy, and then whoop, it switched around where it had a lot of kinetic energy but no potential energy. Let's try this number 25. What type of work is the frictional force doing on the car? People don't push cars as much as they used to. When I was a kid, I felt like we were always getting out to push the car because we'd run out of gas and we have to get out and push it like off to the side of the road, or it'd break down. You have to push it off into the next pull off or whatever. You ever push a car? Who's pushed a car? Like 4 of us, 5 of us? It's a shame. Okay, 6 of us. All right, number 25. Let's stop at 40. Good. B is right. It's B, negative work, because the frictional force is in this direction, but the displacement is in that direction. So remember with work, if the force and the displacement are in opposite directions, then that means that the force is taking energy away from the object. That means that it's doing negative work. If they're in the same direction, that means the force is giving energy to the object, it's causing it to speed up, and that's doing positive work. Let's try number 27. I have a mechanical system that's 40% efficient. If I put in 100 joules of energy, how much work will the system do? How much usable work will it do? I tell my wife that she doesn't like for the car to get really low on gas. She thinks that's inconvenient. So I I always tell her that it's really memorable to run out of gas. That our kids, they've never run out of gas. But as a kid, I remember running out of gas a lot, and it was always kind of fun because you miss school, like you don't get to go to school for the day because you ran out of gas, or it's a very memorable event. And so I tell her that we need to run out of gas sometimes just because to give our kids those memories. She never buys it. It's like, full me some gas. All right, let's stop at 125. Oh, yeah, we need to work on this. So, let's see. Okay, so if the mechanical system is 40% efficient, and I put in 100 joules, that means that I'm going to get out 40 joules. Right? Now, the 60 joules, I lose the 60 joules. Like whatever is left over, I lose. But if it's 40% efficient, that means whatever I put in, I get 40% of that back. And 40% of 100, that's easy, right? 40% of 100 is 40. But that means that I've lost 60 joules. Okay? So 40% efficient means 40% of 100 joules is equal to 40. And this is what I get. This is usable energy. Right? If it's 100% efficient, that means I get everything back, right? That's really what you want, is something that's really close to 100% efficient. But if it's really small, like if it was, say, 5% efficient, then that's bad. I would only get back 5 joules, and I'd lose most of what I put in. Practice those, folks. Those are the questions that people miss, so practice them. You can look back at the other old exams. There's always a question like that. And they're often worded differently, so make sure that you're reading it carefully and understand what the words mean. Okay. Let's try number 30 here, which is larger, TMR or BMR. So you need to know what those mean, TMR and BMR, and the difference between the two. If you finish 30, you can go on to 31. Let's stop at 45, 45. Okay, so TMR is the higher one. Just knowing what the words mean, right? The T in TMR means total. And so the TMR is equal to the BMR plus whatever activity you do. Remember the BMR, the basal metabolic rate, that's just sort of the energy that your body needs to function, to run your big old liver and your heart and your lungs, to run everything. But the TMR, your body also needs energy just to, be active, walk around, do things with your digits. And so the TMR is the sum of the BMR plus whatever you need for that activity. Let's try number 31. Now doing 31. No, don't apologize, it's okay. It's not right, is it? Yeah, that is right. Okay. Let's stop at 55. Good. C is right. Lipids or fats contain about twice the energy density of carbohydrates. So it was 4 kilocalories per kilogram for carbohydrates and for proteins, but lipids or fats have about 9, so almost twice. Let's try number 37. We'll move on to the next chapter soon, but just sort of jog your memory on some of these. Which of these is a way your body responds when it's cold and it needs to be warmer? What do you do when it's cold? All right, let's stop at 50. 50. I like these sorts of questions where I give you a list and you have to pick out the right things. So it's not sweating, right? You don't want to sweat when it's cold out. That's just going to make you colder. Shivering, will that make you warmer? Yes, shivering will make you warmer. Because when your body moves, it just, it's like being more active. It just warms your body up. What about contraction of blood vessels? That's the tricky one. If I contract my blood vessels, does that make me warmer? Yes, because remember, if it contracts, the blood vessels get smaller, and so you get less blood flowing to the skin, and so it's like your body holds on to that heat. If you want to get rid of heat, you open up the blood flow to your skin, and that gets rid of heat. But if you want to hold on to your heat, you keep that blood inside of your body, not up on the surface of your skin. So that is yes. And what about increasing BMR? Yes. So that just sort of makes your body run hotter. So that's C, 2, 3, and 4. Where you go? C is right. What did y'all put A? I love you put A. 2 and 3. Oh yeah, so increasing BMR, that does increase your body temperature. That allows you to create more heat within your body. This makes everything sort of run a little bit faster inside of your body. Okay, let's see. We never talked about this, so you can just put an X to that question. I'm not sure if y'all use these particular things, but I never told you what the Celsius measurement for absolute zero is. It happens to be minus 273, but that's not that important for y'all. Okay? All right, let's go back to our notes. We're going to go on to chapter 4. And we'll have a quiz on this chapter in 1 week, so on Thursday. And it'll cover all the chapters, so make sure that you're reading that. This is on waves. We'll get into sound, and then later in the AMP section, speech and hearing. It's quite interesting, I think the ear is very interesting. Just how the body creates and detects sound is very interesting. Any of you guys, what do they call that? When you do sound stuff with the body. Any of y'all, what is it called? Audiologists. Any of you audiologists, folks? No? Most of you are what? OT, is that right?
Speech therapy.
Speech therapy. OT? OT? They're PTs, right? Radiology. You're PT? All right. So waves. There are lots of different examples of waves. Waves in water. Sound is a wave. Light is a wave. Waves in water, this is called a mechanical wave. I'll write that down later, but let me just sort of preface it right now. This is a mechanical wave. When I say waves in water, like waves going up and down. Other examples of mechanical waves, like you ever did this thing where you hold 2 ropes and you make them go up and down? Like 2 big heavy ropes, do this thing, you know what I'm talking about? Yeah, that's a mechanical wave too. So like if you are doing that, like your athletes say, hey coach, look at this mechanical wave. Y'all do that? Athletes? Y'all do it in training? So lots of different types of mechanical waves. Waves are periodic. That means they repeat. And they are called, so this is really clever, they're called periodic waves. That's what periodic means, just means that they repeat one period after another, and so a wave is called a periodic wave. In a standing wave, the wave travels back and forth through the medium, and then it repeats so that it looks like the wave is not moving. So that's true for your thing with the ropes. Like those are standing waves too. You can make a standing wave too. This is. No, it's not a snake. It's really just a spray. Did y'all think it's a snake? April, can you help me? No, Madeline, can you help me? Just grab the end of that. Can y'all see on the sides? Can you stand up if you can't? So just hold it on the floor there, Madeline. And if can y'all see? So if I do this, there we go. That's a sample. It looks like it's not moving. Sometimes I can get it where it looks like it's just standing still. Just see where it was standing still? Zach, will you come up here and hold it? I'm going to bite you. Okay, so just sort of hold it on the ground. And you just hold it stationary. I'll move it back and forth. Y'all can see okay? Devin, you can see it too? There we go. That's a snake. See how it looks like it's not moving? Sometimes it looks like it's moving. Oh, there we go. But this one just looks like it's just sort of oscillating back and forth, when really there's actually a pulse that's traveling down and then reflecting back and coming back to me. That's called a standing wave. But that's true too when you're doing this thing with the ropes. Those are standing waves as well. All right. Sound waves are periodic. For example, a sound from a guitar is periodic. And we'll talk about these different sound waves. So a guitar has a very complex sound, whereas just a tone, a single tone, has a very simple sound. But they're both periodic, that they have these repeating sounds. A clapping sound is also periodic. So that's a periodic sound. There's a microphone here. That's a periodic sound as well. It's a periodic wave. It's just really, really short. It only repeats for a very small amount of time. So it just lasts for a very short time. Sound waves have a medium. Sound waves have a medium. What is the medium for sound waves? No? No? Air. Yeah, so air is the medium for sound waves. In fact, if you didn't have any air in this room, if I could somehow take all of the air and just suck it out of this room, then you just couldn't hear anything. Even if I was producing sound, so I wouldn't be able to produce sound either because I need air to produce sound in my body. But if I could produce a sound, say with a speaker or whatever, you wouldn't be able to hear it because there would be no medium for it to travel through. That's why there's no sound in space, for example. Like you might produce the sound, but it doesn't go anywhere because it doesn't have a medium to travel through. So all waves require a medium. they cause the sound waves cause the air particles to move side to side. Oh, this should be 2. Side to side. Usually not forward. So I'll show you a video about this later, but if you imagine that I have a speaker that's producing a sound wave, and then I imagine that there are these air molecules all throughout the space in front of it. These air molecules are going to be moving back and forth, oscillating back and forth as that sound wave travels. But this air molecule right here is not going to mysteriously appear over here. It's not going to be pushed forward. It's the same with water waves, right? That if you're out in a boat and you see waves traveling, you know, you have these waves that go up and down, but you don't really have a wave that travels. So if I have a water wave, if I have a water particle that's here, that water particle moves down and then it moves up, down and up. It doesn't move forward, even though it looks like it moves forward. It was true with the spring too, that each point on the spring was fixed in space, but it would move up and down, or not fixed in space, but it didn't move back and forth. Even though it looked like this wave was moving back and forth, the actual spring was staying where it was. Okay? We have 2 different types of waves, transverse and longitudinal. We'll talk first about transverse waves. They make the medium move up and down. I think of a good example of a transverse wave. You want to make a transverse wave? Well, so, raise your hand up like this. Yeah. And then you put them down, and then y'all put your hands up like this. And then you put them down, and then now you. And now. Go back again. All right, so that's a transverse wave. A transverse wave is where the medium, that's you, moves up and down, up and down. That's why they call that phenomenon. Football games, you know what they call that? The wave. Yes, because it's a transverse wave. You should tell your friends, though, next time they say, hey, let's do the wave, you should say, are we going to do a transverse wave or a longitudinal wave? A longitudinal wave is a little bit different. In a longitudinal wave, the medium moves side to side. You might guess now, what is sound? Is sound a transverse or a longitudinal wave? It's a longitudinal, because sound makes those particles move side to side, not up and down like a water wave. So this one's a little bit more tricky if you tell me you want to do a longitudinal wave. So Emily, I'm gonna, like when I'm here, I'm gonna need you and Sarah to reach over and hug one another. Okay, all right? You don't have to hug one another. But then, like you sisters, you could hug one another. And then Sarah, you could hug Alyssa. You could hug Alyssa. It would be called like the hug, not the wave. But then that would be a longitudinal wave. And then all of y'all would hug, and all of y'all would hug. And it would be the medium moving back and forth instead of up and down. That's a good idea, like for football teams. I think that would bring a great sense of togetherness. Yes. Okay? So next time your friend asks you, do you want to do the wave? You say, well, we're going to do a transverse or longitudinal wave. Like, you got to clarify that, because you might not want to do the longitudinal wave with a bunch of strangers. All right? Okay. So longitudinal waves make the medium move side to side. Transverse waves make it move up and down. An example is like the wave at a football game. Where the people move down, and then I'm trying to draw a picture of this. That just looks like a really tall and a short person. You get the idea, up and down. And then the longitudinal wave would be like the hug. Okay. We're going to start something new here. So for simple harmonic motion, there's several things that I want you to know. Simple harmonic motion refers to anytime you have a restoring force. And so we can see this like in a spring. If I have something that's on a spring, say a mass on a spring, I'll use this one for now. I'm going to use this for something else later. But if I have a spring, it has a restoring force. That means that if I pull it back, it's going to go back to its original location. This is the equilibrium position. And if I displace it from that equilibrium position, it'll oscillate back and forth. Okay? So in simple harmonic motion, you always have a restoring force. In this case, the restoring force is the spring. It's from the spring. We'll talk about later where that restoring force comes from for sound, for example. It has to do with the other gas molecules sort of being all sort of stuck in place. But there are several definitions that I want you to know. I want you to know the equilibrium position, and we'll look at graphs of this. The graphs will look something like this, where I have a position versus time. This is my position. This is time on this axis. The position just refers to where is this thing that's oscillating back and forth. So for example, right here, my position, I'm going to call it, I'll call it y, will equal to 0. And that's going to be my equilibrium position. At y equals 0, this is called my equilibrium position. The amplitude refers to how far does the thing displace from its original position. So if I have the spring here, and I have it hanging down like that, that's its equilibrium position right here. That's y equals 0. If I pull it down, this new position is its that new position is the amplitude. So this distance right here is my amplitude. And I measure it on the graph by looking at that value. The period is the time for it to go through a complete cycle. So to start right here, to go down, to go up, and then to come up again, or to go down again. So that is one complete cycle. So this is one period. The variable that we use for this is t. The variable that we use for amplitude is a, and for position we'll either use y or x. We'll sort of switch back and forth on that. For frequency, is going to be f. F is related to the period. In fact, the frequency is the inverse of the period, or 1 over t. So for example, if it takes 2 seconds, if t is equal to 2 seconds, then your frequency is 1 over t, or 1/2 of a second. Or excuse me, not 1/2 a second, sorry. 1/2 of a hertz. I'll give you the units for that soon, I think. I think I did. Hold on, let me make sure. No, I don't see it coming out. Let me go ahead and give it to you now. So the units for frequency is a hertz, like hertz rent-a-car, and that's equal to an inverse second, 1 over seconds, which you can see from the formula here. That frequency is 1 over the period, and the units of period are seconds, so the units of frequency are inverse seconds, or 1 over seconds, and we call that a hertz. We abbreviate it with an H, and then that's my Z. I always put a line to my Z because they look like twos. I've heard of hertz before. If you look at electrical devices, they have frequencies on them because the electricity that we use operates at a certain frequency. We'll talk about that in a later chapter. And then also the pitch of sound is related to its frequency, which is something we'll talk about as well. For sound waves, the speed is not, or excuse me, for sound waves, the speed is set by the medium. And the pitch is related to frequency. So if I have a sound wave, say, in a hot gas or in a cooler gas, which one do you think is going to travel more quickly? You don't know this a priori, but like, you don't have any reason to think, but just intuit it out. If I have a hot gas where the molecules are all moving around really quickly, or a colder gas where the molecules aren't moving around very quickly, in which of those will the sound move more quickly? The hot gas, because the molecules are moving around faster, and so it's easier to sort of move the information along because those molecules are already moving more quickly. And so for sound waves, the speed is very much related upon the medium. And we'll see that too later for solid media, that solid media travel much faster than others. And then the pitch is related to the frequency. You know what pitch is? Like, is it a low or is it a high sounding sound? Hey, try this. It'll blow your mind. I'm serious. You ready? I've been working on this a long time. So I don't know that y'all can do it. Like, it might take you some time to practice. But if you practice, I think that you'll be able to do it. You ready? Now you're just, there's a lot of expectation. Let me make sure I get it right. Low, high. Low, high. Can you do that? Try it. I go and try it. You think you can do it. You think it's so easy. Try it. Anybody else want to try? Low, high. We'll talk about pitch and how it's related to frequency. The speed of a wave, oh, I missed one. I missed something up here. So this is called a history graph. This graph that I drew is called a history graph. And a history graph shows the history of the position for that wave. There's another graph that's really useful that's called a snapshot. And a snapshot would look like this, where I would have the displacement or the position on this side, but here, instead of having the time, I would have x. So the snapshot graph, I often ask for the difference on tests. The snapshot is not a history of the wave. The snapshot is one particular instant in time, and it looks at the wave at that point in time, and it looks the same, but the axes are different. So I'm not looking at the position as it changes over time. I'm looking at the wave as a whole. So like when we have that spring laid out, we take a picture, snap, and then we look at that picture. And this is what that picture looks like. This is useful because it helps us to identify the wavelength. And the wavelength is the distance from here all the way over to here. The wavelength is the distance that the wave travels in one period. This is one wavelength. Lambda is wavelength. It's the distance it travels, distance the wave travels in one period. It looks a lot like the history graph. It looks identical, actually, to the history graph that we had before, except for this x-axis. This is a graph of y versus x. So looking at the wave in 2 dimensions, snap, I take a picture, that's my snapshot graph. The history graph instead looks at a single point on the wave and says, okay, this thing is moving up and then down, up and then down. But this is looking at a lot of different points, taking a picture of the whole wave at one point in time. And so the speed of the wave is dependent upon 2 of these quantities. It's dependent upon the frequency and the wavelength. Oh, but wait, you say. I just said, and you wrote it down, I think, that the speed of the wave is dependent upon what? Remember the hot gas, cold gas? The speed of the wave is dependent upon what? What? The temperature of what? Starts with an M, ends in an M. Medium, right? So the temperature, or excuse me, the speed of the sound wave is dependent upon the medium. Different media will make the sound wave travel at different speeds. But here I'm saying that the speed of the wave is equal to the frequency times the wavelength. That seems kind of strange, right? It seems like I'm contradicting myself. But the speed of the wave is constant. So this thing, V, does not change. It is constant. What changes is the frequency or the wavelength. So the speed of a wave does not depend on either the frequency or the wavelength. It depends only on the medium. So a higher frequency noise will not necessarily have a faster speed. So what I'm saying there is that if I was to increase my frequency, the speed would not increase. The speed would still be the same. And so if that's the case, if I increase the frequency, what's going to happen? If I increase the frequency of a wave, what's going to happen to that wave? The speed doesn't change. What? Not the amplitude, but something else in this equation. The wavelength isn't the amplitude. No, the amplitude will still remain the same. It's going to be the wavelength will change. So if my frequency increases, then the wavelength will decrease. But the speed is always going to remain the same. All right. In air, sound travels at about 340 meters per second. You don't need to know that number, but it's kind of interesting. And then usually in musical, oh yeah, we'll come back to this. Let's go and write it down. In musical instruments, anybody play in the band? What'd y'all play? The trumpet? Trumpet? My son plays the trumpet. I play the tuba. And so the larger the instrument, the lower the frequency of the sound. By the way, that's why men tend to have deeper voices. There are other things too, but men just have a bigger neck area, and so they tend to have lower pitch sounds, lower pitch voices. So the tuba, which is really big, has a low frequency sound. The piccolo, which is really small, has a high frequency sound, similar for a guitar and a bass guitar. The guitar is really small compared to the bass guitar, which is almost a foot longer than a guitar. Okay, y'all have a good day. I'll see you on Tuesday, and we'll have a quiz on Thursday. Cool.